principles. And we want to start, if I have 8 pieces of paper and I number them 1 to 8 and put them in a box, okay, I'm going to pull out a piece of paper, write down the number, put it back in, and pull out another piece of paper. So we're replacing what we pull out. I want to know how many different ways that those two numbers could be added together. Because I pull one out, write the number down, put it back in, pull another one out. How many different ways can those two numbers add up to 12? So let's think about that. If I pulled out a 1, is there any combination of numbers between 1 to 8 that would give me a 12? No. What about if I pulled out a 2? 3. Numbered 1 to 8. 4. Okay, so if I pulled out a 4, what would I have to get to add up to 12? An 8. All right, what about if I pulled out a 5? We could have a 7. What if I pull out a 6? Because I put it back in. I put the number back in. What about if I pull out a 7? And if I pull out an 8? 4. So how many different ways could we, from those pieces of paper, replacing it, those pieces of paper numbered from 1 to 8, how many different ways can we get 12? 5 different ways. All right, let's say we've got a computer that's just randomly generating 2 integers from 1 to 12. Okay, so we've got 2 integers that it just spits out randomly from 1 to 12. How many different ways can we get 2 integers whose sum, we want a sum of 6? So think about that for a minute, and then let's talk about it. See how many different ways you come up with that you could get 2 integers whose sum is 6. So here we get 5 again. If you draw a 1, you would need a 5. If you draw a 2, you would need a 4. If you draw a 3, you would need a, and then you could reverse the order. So yes, there are 5 different ways. All right, now notice these are not necessarily distinct because these are the same number. How about if we had to have distinct pairs? How many different ways? If we had to use distinct pairs. In other words, numbers can't repeat.
With 3? No, 2, right? 2.
Well, if the first one's 1, the second one could be 5. And if the first one's 5, the second one could be 1. That's still distinct. So how many distinct ways? 4. 4 distinct ways. If we go back and think about, I can't spell today. Think about the first example. Say we don't have replacement. I can't put the number back in the box. How many different ways could we come up with 12 on that first example? Okay, we can't put the number back in the, we're just randomly picking a number. First time you pick a 4, and then you pick an 8. Okay, that's one way. You might randomly pick a 5 and then a 7. That's one way. So there's 2. You might randomly pick a 7 and then a 5. How many different ways? You can't put the number back in. Which one are we going to have to eliminate? The 6 and the 6. So how many different ways, in this case distinct ways or without replacement? You're not putting the number back in the box. You're just randomly picking one number and then another number. Okay, so maybe you get a 4 and an 8. Or maybe you get an 8 and a 4. It's just random. So there's 4 ways if we have no replacement. 4 ways without replacement. Or 4 distinct ways because we cannot repeat the 6s. You're not putting that 6 back in. So the difference in that first example and what we just did was with replacement or without replacement. Okay, in the computer-generated numbers, it was whether they were distinct or not. Okay, the first time it didn't have to be distinct numbers. You could spit out a 3 and a 3. But the second time we said, no, we're not going to let it spit out the same number twice. So there were 4 different distinct ways. Make sense?
But they're the same things though. Like if you say without replacement.
A lot of different times you can draw out the picture of what's happening. You know, like we did here, we listed our pairs. But it may not always be easy to list those pairs. And if that's the case, we want to use what's called a fundamental counting principle. And you've probably seen this a long time ago, but I thought today would be a good day to talk about it since you got the Iowa test coming up. You could possibly see something like this. It's really fairly simple. So we want to look at the fundamental counting principle. And basically, the fundamental counting principle says, say you've got 2 different events. You draw one number and then you draw another number. Event 1 is the first number, event 2 is the second number. Okay, but these are usually going to be when you've got a lot of things involved. So you've got event 1, and event 1 could occur in this many different ways. Okay, so our event 1 was how many different ways could you get? 12. That was event 1, and there were 5 different ways if we had with replacement. Okay, event 2, something that's totally independent, might occur in M2 ways. If we want to find the number of ways the 2 events can occur, then we multiply the possibilities for the first event times the possibilities for the second event. For instance, I want to know how many pairs of, how many different pairs I could come up with from letters of the alphabet. How many different pairs of letters from the alphabet are possible? Let's say English alphabet, since we have people that don't always speak English. We don't want to use a Korean alphabet. We want to use the English alphabet. So if we have pairs, that means how many? 2. All right, so let's think about it this way. I have the first possibility and the second possibility. How many do I have to choose from first time? 26. How many do I have to choose from the second time? Okay, it doesn't say that we can't use it again. 26. Because you could have AA. So the number of possible ways that I could get 2 pair, or I could get a pair of letters from the English alphabet is 26 times 26, which is, I think, 676. Combination lock. And it'll open with 3 numbers. Okay, so a combination lock, some combination locks may take more than 3 numbers, but this combination lock opens with 3 numbers. From 1 to 30 inclusive. All right. When I put that term inclusive there, what does that mean to me? I can use 1 and 30. All right, so we've got 3 possibilities. I need 3 different numbers. How many choices do I have for the first number? 30. How many choices do I have for the second number? 30. And how many choices for the third number? 30. So this is going to be 27,000 different possible combinations just with 3 numbers from 1 to 30. If you wanted more possible combinations, you could extend the numbers that you could use, or you could add 4 required numbers. But just with 3 numbers you have to get from 1 to 30, there's 27,000 different combinations that you could come up with. I would not want to have to try to figure out what those 27,000 different combinations were. But this formula helps us to figure out the number of different combinations that we have. All right, let's add a little, yes, sir. This possibility, we have phone numbers have 10 digits, right? The first 3 are an area code. So we want to know how many different phone numbers within an area code are possible, and you cannot start with a 0 or a 1. So I'm looking within the area code, there's 7 digits. Okay, and it cannot start with a 0 or a 1. So we've got our first 3, and then we have 4 more. If it can't start with a 0 or 1, how many possibilities do I have for that first place? 8, because I've taken 2 of them away. Now how many possibilities for the second one? 10. And the third? 10. And then 10, 10, 10, and 10. So we've got 1, 2, 3, 4, 5, 6 zeros, and it's going to be 8 followed by 6 zeros. So we have 8 million numbers that are possible within an area code. It's a lot of numbers. And cities are growing, so of course a lot of people have more than one phone number in their household, but cities are growing at such a rate, they're having to have new area codes added so you can add more numbers for that specific area of the country. Okay, so these that we've looked at, order didn't really make a whole lot of difference. But there are some times when ordering is important, and if order is important, we do permutations. And permutations are not a difficult thing. We'll be looking at permutations today, and then on Tuesday we'll look at some formulas for combination. Now this is an ordering of n elements. For instance, if one element has to be first, if I wanted to check to see how many different ways people could come into the room. One person comes first, then there's less to choose from for the second place, and less to choose from the third place. So an example of that, if I have these letters, and I want to figure out how many possible orders there are, or permutations for these letters. Permutation means that order's important. How many different ways could I order these letters? Well, we've got 1, 2, 3, 6 letters. How many possibilities for that first space? 6. Okay, so I've used 6. How many possibilities for the next one? 5, because we've used one of them. And then how many for the next one? 4, and then 3, and 1. So another way that we could write this in a simpler fashion is 6 factorial. It looks like an explanation point, and you've probably seen it on some tests, but that means 6 factorial, which is 6 times 6 minus 1 times 6 minus 2 times 6 minus 3, just as we have it written out here. So we could multiply these all together.
I think it's been on the Iowa before.
You probably have seen it. You might not have remembered what it was, but that's what it means, is if you see in factorial.
I think I was like, I think someone
Okay, shh. In factorial just simply means that that's going to be n times n minus 1 times n minus 2 times n minus 3, all the way down to just 1. That's what that means. So what is 6 times 5 times 4 times 3 times 2 times 1? 720. All right. How many different ways could we line up 8 children? In how many different ways? Can we line up 8 children in a row? Well, that's 8 factorial, or 8 possibilities for the first place, then 7, then 6, then 5, then 4, then 3, then 2, then 1. Those are the number of ways that we could line up 8 children or 8 students. So that is, anybody got it?
40,320.
40,320. How many different ways could 8 horses come in first, second, and third? So if this is an example of taking, you have n elements, take an r at a time. In fact, you're not using all of those elements. Okay, we've got 5 more minutes before lunch. All right, so horse race, you got 8 horses, but only 3 win, place, and show. That's the only way you get any money, is if they come in first, second, or third. So how many ways for the first place? How many possibilities for first place horse? 8. How many for the second place horse?
7.
And the third place horse?
6.
So for those 8 horses, 42 times 8, 16. Is it 336? 336 ways out of those 8 horses that you could get first, second, and third. And if I'm not mistaken, I haven't been to a horse race in eons. To get the big prize, don't you have to name all of them in order? First, second, and third? I don't know. There may be an extra prize for that, but for extra money.
bid on the one that's gonna win.
Yeah, you mainly want first place, but anyway, that's how you could do that. One way that can be shown is NPR, or 8 horses taken 3 at a time. The formula for that, again, your calculator will do it, but you don't always have a calculator on all of your tests available. So the calculator, the formula is n factorial over n minus r factorial. So if we're going back to our 8 horses 3 at a time, that's 8 factorial over 8 minus 3 factorial. And that would be 8 times 7 times 6 times, if I'm going to have 5 factorial in the bottom, what's going to happen to that? Everything else cancels out, doesn't it? So you could stop it right there, and you have your 8 times 7 times 6, which we said was 336. Right, so, okay, the assignment is on page 696. You may have to look at a little bit to answer all of 1 through 4. And then 8 to 26 even. All right.